All right, good morning, and welcome to our virtual session today. Let me go back. So let me just double check everything's working fine. Haven't streamed from home in a while. Looks like the audio was maybe a little high, so I've tuned that. And as soon as anybody joins, please let me know how things are looking. Okay, I think I'm all set now. All right, so this is the Exam 2 recap session. As a reminder, this is taking place of our lecture on Tuesday, November 25th. So we will not have a lecture that day. This is for EVEG 3110, water and wastewater treatment. And I'm going to go through the exam solutions with you today. Okay, so just a first few notes here. Of course, as usual, my grading scheme is to be rather generous with partial credit. If I see you made a significant error, that's about 25% of the possible score on a particular free response question. A minor mistake, like a flipped negative sign, that would be probably about 10%. So the grade distribution came out as you see. Average was about 81.5, and we had quite a few B pluses, as we see. So that's the deal. I did not end up curving that at all. And this is for, these are showing the non-makeup exams. I mentioned the makeup exams were quite difficult, so I added 10 points to each of those. And still the average was less than what we see here. Okay, so if you had a makeup exam, of course, maybe this is still helpful to study to see what was on the regular exam, but feel free to contact me if you'd like to discuss those solutions. For those of you who submitted an online, had the alternate testing, I apologize, I haven't returned those just yet. I will email those as soon as I'm done here. Okay, so let's get into it. And again, please feel free to chat to me. As far as I can tell, things are looking good on my end, but you let me know if there's you see any issues. You can of course adjust things as we go. Okay, so the first section would be the true or false and multiple choice questions. First question up was a true or false statement. Granular filters operate primarily on the basis of size exclusion of particles. So when we're removing particles with a granular filter, it is not necessarily size exclusion. That does happen a little bit, but it is primarily other sticky forces like adsorption. There are impaction, sedimentation, all of that. It's not primarily on size exclusion, therefore that one's false. Next up, which of the following is not a reason to terminate the production phase of a granular filter? So which one would not trigger a backwashing step? Head loss is a common way to do it. Turbidity in the influent doesn't really matter. It's supposed to be removing that. It would be the turbidity in the effluent that would cause a stop of treatment. In the influent, that's going to be variable. Maybe it's a concern, but it's really what's in the effluent that matters. Okay, next up, what basis does the equation we use to calculate the filter efficiency, what basis of efficiency does that filter efficiency equation use? And you could look at it, and it's the volume filtered divided by, minus the volume backwashed, volume rinsed, divided by the volume filtered. So this equation has a bunch of volume units. And so it is efficiency on the basis of water. How much water we used would be the correct answer there. It is not necessarily energy, not necessarily time. If we backwash really, really fast, that would have the same efficiency as something that backwashed really slowly, even though the time would be different. if you use the same amount of water for each. Okay, next up, true or false, membrane filters operate primarily on the basis of size exclusion for particles. This one would be true for the removal of particles. If we get so small that we're doing things that we don't call particles, like molecules, perhaps we can consider some other answer there, but in general, we would consider that as true for particles for membranes. Okay, next up, which of the following is not an example of a typical material used for a membrane in water treatment systems? So basically, what can we make membranes out of, or what can we not make them out of? So the examples are cellulose, PVC, stainless steel, and ceramic. All of these except stainless steel are commonly used. I don't think we can manage a very fine pore structure on a stainless steel thing without exposing it to rust. Even though it's stainless, there's still quite a bit of potential for rust, so maybe a stainless steel apparatus would hold a filter, but the membrane itself would not be made out of stainless steel. So that's the best answer there. Next, when calculating a membrane's flux, which flow rate should be used? When we're talking about flux across a membrane, it's exactly that. It's the amount of water going across the membrane. Therefore, what we need to do is take a look at what is permeating through the membrane. It's not necessarily the feed, the retentate, it's not the total. And while maybe you could consider some other metric, permeate really is the best answer here. Okay, next, in the context of this class, which of the following is the best description of Jon Snow? We covered that. That's, and in fact, if you answered some of the other funny ones, maybe I gave you some partial credit, but the father of epidemiology is the guy we're referring to. He famously attributed water quality to the cholera outbreak as the source issue. Okay, next up, we have another true or false. OCl minus is a stronger disinfectant than HOCl. This is false. HOCl is the strong one. So HOCl would be the strongest disinfectant. Okay, last of the true or false and multiple choice, we have which of the following is the best description of the reaction kinetics in the Chick-Watson model for disinfection. And if we recall, this is referring to the fact that we would describe dN dt, for example, as negative K, our coefficient of specific lethality, times C, the concentration of our disinfectant, to the n power, times n to the first power. And when we describe it, we say pseudo first order because there's actually two things that could change. The C and the n could be changing. But we take the concentration of the disinfectant as a constant, then this one changes. And with respect to this one, we have the order of 1. So in that sense, we say this is pseudo first order with respect to pathogen concentration. So if you answered disinfectant concentration, you were fairly close. If you answered C, you were fairly close, but you missed the fact that it's changing with respect to N. The rate depends on how much N is there. All right. From there, we get to the free response questions. And the first one is a membrane problem. And part A says, asks you to draw a diagram using the relevant flows for a cell operating with cross-flow filtration mode. And I gave you a reminder saying that there are 3 possible flows. We have feed, permeate, and retentate. So we have Q feed. And I'm going to draw this as some filtration cell, pretty arbitrary. And I'm going to draw a line across as the membrane. So anything that crosses that membrane permeates through it. And that's how I'm going to draw and describe my flows. So what passes through would be the Q permeate. And what is rejected is the Q retentate. So I was looking for simply this, something very simple. Some of you recalled some other diagrams we had taken a look at, perhaps a cross-flow system that looked like this, where we drew some membrane here, and then you had permeate going through there, and this would be your QR. This would also be acceptable. Really what I'm looking for is to see that you are tracking the water flows and what is going across, passing through the membrane, and what is being rejected by the membrane. That's what I was concerned with. Next up, this was even simpler. Unfortunately, some of you are getting a little confused at this one. To do the same thing, but in a dead-end mode, it would simply look, and you could draw it a few ways. In class, I tended to draw it vertically to say we have some Q feed happening and some membrane here, maybe just a line if you wanted, however you'd like to draw that. What passes over it would be the, excuse me, you know what, I'm going to draw this a little different too. So if we add water there, what passes through it would be our permeate, and if we have anything remaining, it's not a flow, but we would have a retentate. This is completely optional to draw because I did not ask you to draw volumes, I only asked you to draw the flows, right? So if you drew a flow that corresponded to a retentate, you did it wrong because there is no retentate flow. But if you labeled it, it would look something like that. Okay, so next up we have this filter. Now we give it some task to do. So it says initially the filter is operated in the dead-end filtration mode. And if the initial concentration of algae is 3.5 times 10 to the 5th cells per liter, the volume is 500 milliliters, what is the concentration of algae in the feed of the solution, if 350 milliliters of the solution is passed through the membrane. So given this, and by the way, we could also write this, you could do it this way with a membrane here, or you could even put the membrane here, as long as you're labeling in the same manner consistently, then it works just fine. I'm going to redraw this a little bit. Get rid of this one. There we go. Okay. Okay, so either one of those drawings would be fine. Then that's relevant because in part C, we want to consider the case where we had some amount of volume, half a liter. So initially we had 500 milliliters, call that V initial, and then we pass 350 milliliters through, and so we have some V remaining, or V retentate. I'm just going to call that VR. This should be 150 milliliters, or 0.15 liters. So just simply drawing up the settings here is extremely important, as you'll see. Okay, so then the problem earlier said that we have 0.55% rejection of the algae. So not many algae cells are being rejected. Most of them are passing straight through the membrane. And so we need to solve. We can take a look and find our initial number concentration of cells. So we'll call this N naught. This would be 1.75 times 10 to the 5th cells. So this is going to be the initial number, not even number concentration. And in fact, because we often use the N as number concentration, I'm just going to put this as a number here. So the initial number is 1.75 times 10 to the 5th cells. Now, when we reject some of the cells, we are going to remove them from the amount of water that we filtered. So the 0.55% rejected applies to the 350 milliliters filtered. So that would be 0.35 liters. So we can find the number of cells rejected. And we can get that, or you know what, we can actually look at the number of cells in the solution after we've done the filtration. We can get that by taking our number of cells that would still be remaining in the 150 milliliters, just plain and simple. That's how many would be there without any filtration or without anything. It's the concentration, right? The cells per volume we could find as the concentration initial times 0.15 liters. That's literally just saying if we discarded some water, we're left with some water with stuff in it. Okay, so we just didn't change anything. That's the amount that would be remaining without any rejection. Then we're going to add to this the number that were rejected from that 350 milliliters. So we'll take that 350 milliliters, multiply this by the 0.0055, that's our 0.55%, and then multiply that by the concentration, the initial concentration, N naught. So the N naught is the 3.5 times 10 to the 5th cells per liter. Okay, so doing that, we get some number of cells in the final solution, and that should come out to be 5.32 times 10 to the 4th cells. And then we can treat that, divide that by the 150 milliliters remaining and get a value of 3.54 times 10 to the 5th cells per liter. What we'll notice is there's a small increase in the number of cells that we have there. So we used to have 3.5, now we have 3.54 times 10 to the 5th. All right. And by not participating live, you guys are going to make this really quick because nobody's here to ask questions. Okay. And pro tip, you can always watch on fast forward mode if it's not fast enough, or you could slow it down, watch slower if it is too slow when you watch the replay. Okay, so later, the membrane apparatus is changed to operate in a cross-flow regime. After several hours, the membrane becomes fouled and the rejection increases to 80%. So this membrane was designed maybe with it in mind that it's not going to reject many cells at first, but with some operation, it clogs up a little bit and then it starts filtering out pretty well. So now the rejection reaches 80%, that is our uppercase R, or we could say this should be 0.80, and we have an equation for that. That's 1 minus the amount that's permeating, or the fraction that permeates. So that'll be 1 minus Cp over Cf. It goes on to say if you apply a flow of 2.6 liters per hour, and the recovery, which is the lowercase r, is 90%. What is the concentration of algae in the permeate stream? So we want to find Cp. That's our task. And if we take a look from the information given, you could pause and consider what R means in terms of the flows. But actually, what I already wrote gives us a way to solve for CP, and we happen to know CF already, so it actually becomes just that simple. We can say, we can add CP over CF to both sides and subtract 0.8 from both sides. That'll give us CP over CF equals 0.2. So CP will be 20% of CF. As simple as that. That comes out to be 1/5 of 35 is 7. And if we count it as 35 times 10 to the 4th, that might make sense. So that becomes 7 times 10 to the 4th cells per liter as our answer. So quite straightforward on that one. The only trick would be if you didn't recognize the fact that this part was not needed. Neither was this. So didn't have to do much fancy. There was more than enough information provided, kind of giving you the context, or more than enough context there. All right, next up we have a Halloween special. So imagine that this Halloween turned out to be quite a bit scarier. Of course, I'm grading this a little late, so sorry about that, but quite a bit scarier than you ever imagined. Everyone who dressed up as zombies actually became zombies and infected most of the world. After miraculously surviving the ordeal and finding a safe shelter, you realize you need clean drinking water, of course, of all things. Not what you see in the movies, right? More than just about anything else. You have plenty of water from a local bayou, but it's muddy, and you decide to improvise and make a makeshift sand filtration unit out of a bathtub that has approximate dimensions of 0.65 meters by 1.75 meters. Given that the system is not ideal, you are limited to a loading rate of 0.57 liters per square meter per minute. Answer the following questions about the setup. So part A says how much water would be produced after 12 hours of filtration, no interruptions, no backwashing or anything like that. Okay, so let's get a few things out of the way first. We can go ahead and calculate the area of this filter. The length times the width should give us 1.1375 square meters. Time of filtration that we're going to take a look at here, simply 12 hours. Of course, we can convert that to minutes, 720 minutes there. To calculate the volume, really all we need to do is recognize that this is going to be the loading rate, VA, times the time that we are filtering, multiplied by the area of the filter. Put all these together, you'll notice this is meters per second or something like that, a volume per area per time, multiplied by area. So if we check the units, make sure everything's good, we have square meters here. Our VA, just as a side note, was given. This is 0.057 liters per square meter per minute. So it's good that we have time in minutes. Put all these things together, we should get 46.68 liters. Of course, you could have solved this for cubic meters. That would have been 0.0467, if you round that last place, cubic meters of water. Okay, part B says instead of backwashing, you decide that it's actually more practical just to simply replace the sand when it gets too clogged, and you're just going to have to find the sand and load it up, dump the other stuff. So it takes a little bit of time to do that, but you don't use any water losing it. So what I was looking for you to notice here, based on the context of this question, is that the VB equals 0. Even though it does take some time to do it, and that will affect the total cycle time. The total cycle time is 14 days. Then we have time for rinsing. That would be the 8 hours. And then we have the time for backwashing, but this is just simply replacing the sand. So I'll just call this T sand. You might call it TB, but you don't want to mislead yourself thinking that you're actually making some volume of backwash water. Regardless, it's taking some time, so that's going to be 6 hours. Another thing we can do is put all of these into minute values. TF, of course, will be the total cycle time minus the losses from the time for rinsing and the time for replacing the sand. So if we put the 14 days into minutes, this should be 20,160 minutes. Time for the rinsing to 8 hours should be 480 minutes. And the 6 hours becomes 360 minutes. That would give us a filtration time, TF, equal to 19,320 minutes. Okay, we need all of that so that we can get the volumes produced in each scenario so that we can solve for the loading rate, which is given, so the effective loading rate is given as V filtered minus VB minus VR all over the area of the filter times the total cycle time. We know this goes to 0, and so really we need to find, we have the area of the filter, we now know the cycle time, and we just simply need the VF and the VR. So just like we did in the part A, we're going to put in our numbers for the loading rate that was given to find VF and the area that we know. The volume filtered comes out to be 1,253 liters, and the volume rinsed comes out to be 31.12 liters. Practically speaking, that might not be enough, but I don't know. I think trusting some random bathtub full of sand, I'd probably filter some more. Anyhow, we put in these numbers, we take the REF, the effective loading rate, and we expect this should be a little smaller than what we started with. And if you recall what we started with, so the loading rate itself was 0.057 liters per square meter per minute. So it would make a lot of sense to me to use those same units for our loading rate, but of course you could have chosen some other units. So this should be 0.053 liters per square meter per minute. Of course, you could have put that into cubic meters. That would have been 1,000 times smaller. And I apologize, I think one of my dog's hairs in my face, attacking me. You could have also put it in terms of hours, 3.18 liters per square meter per hour. So this is my favorite answer, but I would have accepted some others. Could have even done days. I don't know if anybody did, but technically you could look at 76.32 liters per square meter per day. And any of those with cubic meters on top instead, or meters per time. One thing I'll note is some people got this wrong, but close. So several people calculated some wrong answers. In a couple of manners, largely if you had VB was not 0. And I was checking this because this would give you some values that were like 0.0546 liters per square meter per minute. And you'll notice normally this is close enough that I would give you full credit and not think twice about it. However, you got a very important part of the problem wrong, so I was taking off credit for getting the answer wrong, technically wrong, because you used the wrong procedure. So what I was checking is, did you appropriately count VB as 0? So if you got it close, you will have recognized that the fact that we weren't taking much, like if you used a loading rate and used that 6 hours, that would not be a lot of water, that would not impact your effective loading rate by a lot, given that this is a 14-day cycle. But you were still solving the wrong problem or providing the wrong procedure for it. So if you got points off and you felt like you were very close, check on that, because that's the reason I was taking off points. Okay, so then that brings us to our last problem, where we're going to compare a plug flow reactor and a CSTR for use in disinfection operations. And we have a reactor that's being designed with a criterion for achieving a 3-log reduction. Side note, that is 99.9% removal. So let's go ahead and get that clear right now. That would also correspond to a fraction of 0.999, or 0.001 as a fraction remaining, 0.1%. And we describe the fraction remaining as N over N naught, or C over C naught. Okay, so continuing. So we need to remove that much cryptosporidium using ozone as a disinfectant, which has a coefficient of specific lethality of 1.75 liters per milligram per minute. We assume that the coefficient of dilution is 1, and if the flow rate of the process is 0.1 cubic meters per second, and the ozone is applied at a concentration of 0.42 milligrams per liter, we got to answer the following questions. So our C to the N is simply 0.42 to the 1 power milligrams per liter. So part A says, what fraction of cryptosporidium will a CSTR with a 25 cubic meter volume remove? And if I'm not mistaken, I gave you something very similar on your homework, so I was hoping that in general you would do pretty well here. We also know K was given at 1.75 liters per milligram per minute. This means we could calculate our K star, which is simply K times C to that N power. And if we put these two together, we will get a K star of 0.735 per minute. Okay, that will be a nice springboard for the rest of our problem. So we need to find what fraction of crypto will this remove if we have a CSTR. So what we're looking for is really 1 minus the amount remaining. So we're going to set this up to solve for N over N naught, and then take 1 minus that to get our final answer. Now for a CSTR, might be helpful to draw this, of course. As always, we would have a mixed system with water coming in and going out, Qn not coming in, Qn leaving, with some volume there. And we can set up our mass balance in that volume as a steady state system with Qn not coming in minus Qn going out, plus our reaction term, which is going to be a decay in that volume corresponding to K star times N to the 1 power. So VKN over there. Now, we've done that a bunch of times, so I'm going to trust that you remember and can do the algebra to resolve this and solve it in terms of N over N naught. You can divide everything by Q, get it in terms of theta. We should get N over N naught equals 1 over 1 plus theta K star. You could also just leave it as theta KC here. With that, we also recognize that we have values for our volume and our, so in this case, volume, what we're testing here is 25 cubic meters, and our flow rate was given at 0.1 cubic meters per second. So that means our theta for this scenario, theta is simply V over Q, 250 seconds. So we now have everything to solve for the n over n naught. That would be 0.246. That's the fraction remaining. So if you left your answer there, you were not quite finished. So 1 minus 0.246 gives us 0.754, or 75.4% removal. That would be the correct answer. Okay, so what I was looking for is to see that, to make sure you got the CSTR portion correct. You would also need to make sure you were navigating the K times C appropriately, handling your theta, all of that. And then the last step would be the 1 minus the n over n naught to get your correct answer. You also had to recognize that what we're really looking for was the 99.9%, as that was not strictly the case for this particular system. That was just the target. So we're kind of checking this number to see how close we get to that 99%. So we're designing a system, we're going to design a system that achieves that, and we're testing to see, okay, well, how close does this CSTR get with a 25 cubic meter volume, and then how close does a plug flow reactor get? So speaking of the plug flow reactor, again, maybe it would help to draw that up. Plug flows are a bit simpler in a sense. And we're going to treat this largely in the case like we would for a batch reactor, where we have dN dt in some volume would be equal to, in that volume, the reaction rate, which would be the negative V K star n. This we can derive from there, as we've done a bunch of times. N over n naught should come out to be e to the minus k star, and instead of time, we're going to put theta, right? Theta is going to be the same because the volume is the same here, the flow rate is the same, so this is still 250 seconds. So with that, we already have k star, we solved it earlier, we just simply need to put in the numbers. And in this scenario, n over n naught is equal to 0.04677. So then 1 minus n over n naught to get our real answer would be 0.953, or you can write that as 95.3% removal. Or that much removed. Okay, so we can see we are getting close to our 3 log removal, but we are actually not even quite at a 2 log removal, which would be 99%. So we need to have something larger. To achieve the 3 log removal, we know that this is greater than, the volume that we need is greater than 25 cubic meters. And the way to find it is actually relatively simple. We just simply need to set the n over n naught. This must be 0.001 now. And we can say then how to find our volume. Well, we know theta is going to change with volume, V over Q. So we can rearrange this a little bit to say, well, we'll come back to that. We're going to solve for volume given some theta. So let's take then this form, the natural log of 0.001, to get rid of the e to the minus k, the e to the power of. We can get rid of that by simply taking the natural log of both sides, and then we get the natural log of 0.001 equals negative k star, which we know, times our theta, which is v over q. So we can solve for v and say the volume is going to be we'll go ahead and divide both sides by the negative and the k, and multiply both sides by the q. So we can get V equals Q times, so we'll say negative Q times the natural log of 0.001 divided by K star, which we solved earlier. When we put in those numbers, we will get a volume here of 56.39 cubic meters. Okay, and that'll do it. So if there are any questions from the couple of viewers that are here, happy to answer. Otherwise, that's it. And again, no class on Tuesday. This takes the place, and have a happy Thanksgiving. All right, that'll do it.